I'm Charles. I'll be presenting the work configuration testing of flight software. This is work done at Fraunhofer, USA, Center for Experimental Software Engineering, working with the core flight software team at Goddard. So the motivation for this work is that flight software is configurable. And that's been mentioned many times throughout this workshop. So the users of the flight software can select different values for the configuration options and for the specific missions and the hardware platforms that it runs on. So writing software this way allows the code, the flight software code, to be reusable, portable, and extensible. So those are the advantages. But another characteristic of flight software is that it's also mission critical. So if anything goes wrong during the mission, the consequences are very bad. So the flight software needs to be extensively tested and needs to be as close to bug-free as possible. But here lies the problem. The configuration space, that is the unique combinations of all the configuration options that's possible, grows exponentially to the number of options. And because in theory, every configuration should be tested to assure mission-critical safety, this is a tremendously large number of configurations to test. The system under test is the core flight software, and is no different. It faces the same problem. Dave has mentioned this yesterday during his talk about CFS, that it has many configuration options. So I'll just briefly go over what the core flight software is. So it's developed in this product line style. It's designed to be mission independent and platform independent. And various flight software missions will build their flight software on top of the CFS, such as the GPM mission. The CFS is highly configurable with hundreds of different options. The way to set these options, for example, is in this one of the header files is the CFE platform config headers. You can set things like the memory pool size, the maximum pipe depth, and the maximum event filter. So this, each of these and many more options could be Boolean, could be integer values, and that can easily result in billions of different configurations. And it's definitely impossible to test them all. So, but you still need to assure software quality, right? So bugs can cause problems from any combinations of these option settings. It could be setting the pipe depth to 135 and then the event filter to 1200. Or it could be some other combination and so on. And you could have a long, long list of different combinations. So how do you ensure you can test every possible, how do you ensure that every combination is bug-free? Well, the good news is that flight software and configurable software in general are not written in a way that every single combination will produce a unique behavior in the system. Behavior here could be code coverage, could be test case failure and passing reports, and could be system crashes or hangs. So the goal of this research initially was to test only configurations that will produce different behaviors in the system. That is, we define the effective configuration space to be the minimum set of configurations needed to execute all the system behaviors that's in the flight software. But that turned out to be a pretty difficult problem to solve. So we relaxed the rule a little bit. So we're aiming for a more practical goal. And that is to efficiently approximate the effective configuration space of the software. So how does it do that? So this comes to the concept of configuration interactions. These things called interactions can really tell us about the effective configuration space of the software. We define interactions as certain combinations of option settings that will reveal different behaviors of the software. So let's take a look at this very simple piece of sample code here with 3 Boolean configuration options. So, and we're looking at the software behavior as complete line coverage. So it's very easy to see here that only 2 unique combinations of option setting actually make a difference in the system in terms of this behavior we're looking at. You have to set A and B to true, and you have to set A, B, and C to be true. So we call these interactions. And we define the strength of an interaction to be the number of options that are participating in the interaction. So for example, the last interaction here has 3 variables, therefore it has a strength of 3. So as you can see here, even though there are 8 potential configurations in order to guarantee complete coverage of the software system during test, there are only 2 interactions. And in fact, these 2 interactions can be covered by a single configuration. So you went from 8 configurations you want to test through a naive black box approach, or you can look through the code and find clues, and that will narrow your testing effort down to 1 configuration. So how do we find these interactions? We actually conducted a very extensive study on the configuration space of configuration softwares in general. And this is the reference for the work that we've done using a static analysis technique called symbolic execution to go through, exhaustively go through a software's execution path and produce sound results to make these 3 very important observations. So the observations we made in this work is that first, the interactions are actually very rare. Despite you have hundreds and thousands of different configuration options with many different values you can set, the number of interactions are actually quite small. And they tend to have low strength, meaning only a few configuration options interact with each other to produce unique behaviors in the software at a given time. The next observation we made was most of the system behavior can be executed or observed at low strength using only a few different combinations of option settings. And finally, the higher strength interaction, that is the 5-way, the 7-way interactions with many more options, they tend to include the lower strength interactions. So this will give us a clue of how to find the higher, much harder to find higher strength interactions using the clues that from the lower strength ones. So this will, based on these observations, we created a new algorithm called the interaction tree discovery, or iTree for short. So this iTree approach uses a iterative strategy to search through the configuration space for the effective configurations during testing. So it takes this, so during the first iteration, it will generate a very small configuration sample using various different types of techniques to observe system behavior in general. And these samples tend to be able to execute the most of the system behavior because the interactions are low strength. And then we take these execution profiles and feed it through our machine learning algorithm to discover potential configuration interactions based on the execution of this, the observation of the system behavior. And then for the future iterations, we narrow the search space of the configuration space by using the knowledge discovered here, using the interactions, so that it will progressively get better as the testing process continues, as it gets more information about the system's configuration space, and it will become more and more effective in covering the very difficult to find behaviors. So at the heart of this approach is a data structure called the interaction tree. This is the internal model that the iTree algorithm built as it tests the system. So this is a hierarchical structure of the system's configurations. So I'll just quickly go over how the iTree goes through a typical testing session to discover information. So initially, the interaction tree only has a root node with the interaction true representing the empty setting, because at this point, we don't know anything about the system's configuration space. It will generate a configuration sample. In our implementation, we used a technique called the covering arrays. So this basically says you have a configuration model with 4 variables, and the first configuration will set A to 1, B to 1, C, and D to 0, and so on. So this iTree algorithm will take this set of configurations, it will run the system and the test suite under this set of configurations and collect the execution information. After that, it will take the execution information and feed it through a machine learning algorithm and try to discover interactions that are responsible, well, the combinations of option setting responsible for the different behaviors. So these are approximation of these combinations of option settings. And we'll add them to this interaction tree. So now, for the future iteration, now we have more clues to go on. And we use heuristics to pick the next interaction in the tree that will give you the most bang for the buck for the next set of testing efforts. So in this case, through the heuristics, it will pick the middle node here. Now, from this second iteration of testing, it will generate another configuration sample. However, this time the sample is fixed with the values consistent with this interaction. So A and B values are fixed. And this essentially narrows down the search space. Now you can see here, because we're only sampling in the C and D value space, we effectively sampled all the combinations using only 4 configurations. And any interactions discovered in this process will automatically be added to the interaction tree because it's in this subspace where A and B equals 0, and then you can further divide, and then you can go on to the tree, and the algorithm could backtrack if it fails to discover any new interactions to continue with the testing. So this is a very quick overview. So iTree was actually developed for another publication here at the University of Maryland. So we empirically evaluated iTree on several industrial systems before we applied it to the flight software. So we tested on 3 systems here, VSFTPD, which is a secure FTP server shipped with Red Hat Linux, NGRCD, the next generation IRC server, and also for our scalability test for iTree, we performed it on MySQL, the open source database, with about 1 million lines of C and C++ code. So if you want more details on the implementation of iTree, here's the reference. So from this paper, we measured the effectiveness of iTree, and it turns out that iTree can outperform any existing approach. It can achieve higher coverage than existing approaches using 3 to 4 times fewer configurations than the other approaches. In addition, during the testing process, we tend to execute more of the system behavior at the early stages of the testing process than the existing approaches as well. And another added benefit, because of using this machine learning technique, the iTree automatically detects when you have performed enough testing, whereas the other approaches you have to kind of guess. iTree will automatically stop if you cannot find any more configuration interactions from the behavior. You can't distinguish any of the behaviors from a particular cluster anymore. And the final thing is because we're doing this using a dynamic approach instead of a static analysis approach, it's programming language independent, as long as you can define a way to observe the system behavior that you're interested in during your testing session. iTree not only performs testing on your system in a way that is complete, it will actually tell you potential combinations of option settings that's responsible for different behaviors. So for example, if you run into a problem where the system is crashing, and if you can find the cluster of configurations that's causing it, iTree will actually tell you the combinations of option settings that's causing the system to hang. No other existing approaches can do such thing in a practical way. So in our previous work, we performed the static analysis, which is very expensive. We ran it on about 40 machines for several weeks to calculate this kind of information. iTree did it in about 20 minutes. And this is on top of performing the testing while doing the intelligent gathering as well. And we verified the results against our static analysis tool. And it turned out 95% of the information we discovered were exact match to the static analysis tool. iTree is also scalable. We designed it to be scalable because even though it can effectively approximate the effective configuration space, it still requires a lot of testing because this configuration issue essentially adds another dimension to your testing. Not only do you need to run all your test cases, now you need to run all your test cases on all the configurations you just selected for testing. So it's very essential to have a system that can handle large amount of test case / configuration combinations to run. So we need to parallelize the configuration testing to make this approach practical. So what we did was we integrated iTree algorithm into an existing research project, SCO, Distributed Continuous Quality Assurance process and framework that was developed at University of Maryland. Basically, the iTree will be the brain of this framework. It will assign configurations to the SCO framework for testing. And then the SCO framework will execute the test and then retrieve the results and send it back to iTree for analysis. So this approach is quite fast, robust, and available. We designed it to, it was designed to support configuration testing. It has supported numerous research projects at the University of Maryland. And for the iTree testing of the MySQL, at the peak, we used about 100 cluster machines to test the MySQL regression test suites in parallel. This is a diagram of what the integration looks like. So you have the iTree here through API calls going into the server side. This API call is actually quite flexible. You can implement your own set of API calls to integrate with your own testing framework if you want to. And then the SCO server and test queue will assign different cluster machines, and you can actually have volunteers participating in the SCO projects. All they have to do is download a Perl or a Java client. Everything else will be taken care of. the server will tell the clients exactly which steps you need to compile, instrument, to run the test cases, and so on for the testing process. That was the iTree. Now we're going to go into testing the core flight software using iTree. This is actually a preliminary results for configuration testing on flight software. We executed the CFE, the core flight executive, using the set of stubs and the unit test that's provided by the core flight software team. They have done a really nice job isolating the compilation, the instrumentation using Gcov, and running of the unit tests in a very nice build file. So it made our jobs much easier to integrate CFE into the scope process. We defined a configuration space using about 40 configuration options from the platform config header files here. So for the option settings, we picked the minimum, the default, and the max values for each options. So these are all valid values for the configuration options. And then we created an automatic configuration file generator that will generate a valid configuration file for compilation for the scope process, so that the iTree will dictate this is the configuration you want to test. This generator will create a valid configuration file for this configuration. The scope process will take the file, take the source file, compile it, instrument it, and run it, and send the results back. So the configuration testing of CFE was also done on the scope in parallel. So here is our findings through this preliminary results. So we found several critical issues during the testing. This is just a single run of iTree, and we were able to find about 8 different issues that will cause core dumps and systems to hang. And notice this report here. Not only did we tell which module the failure was at, what the bug or the issue was, we also tell the team that this is the configuration option that caused the problem. And this is the option setting that caused the problem. Excuse me. And because we're using only the stubs and the unit test, the system behavior we can observe is limited. So that's why the reports only shows this one-way interaction where only one configuration option is causing the problem. But as we expand into using the actual libraries and using more extensive test cases and include more values and more options, there will be more sophisticated issues that will involve more options. So for MySQL and VSFTPD, we actually found unique behaviors using up to 7 different options set in a very specific way in order to see a behavior in the system. So just to wrap it up, for future work, I mentioned we want to replace the stubs with the actual system calls. I think we'll be able to observe a lot more system behavior for the machine learning algorithm to actually cluster and learn about the system. We want to increase the number of options and their settings. Right now for the system, we're observing only the line coverage of the system, and then using post-analysis to actually map this line coverage profile into a hang or a core dump. Each of these bugs actually have a very unique line coverage profile that's very easy to identify. But we would like to extend it into observing passing and failing test cases. In our previous research, we have actually shown that test cases can pass in some configurations, but then fail in others. We also want to include other performance metrics that, for example, if you want to tune your system or find a specific configuration that's very good for performance, iTree can perform that kind of analysis as well. And we also would love to apply iTree on more NASA flight software. So if you're interested, here's my contact at the end of the slides. So before I end, I just want to acknowledge that we want to thank Lisa Montgomery for heading the NASA START project that's funding this applied research, and also Sally Godfrey from the Goddard Flight Center. So I'll take any questions you have right now. Yes, we filed a bug report. We haven't followed up on whether they have been fixed or not, but they're definitely valid bugs. Yeah. Yes.
We haven't had a chance to look at those specific issues yet. I mean, we've got them in our tracking system. Mm-hmm. But I guess one question that just didn't come up before when I talked to you. Do you know that it was not the unit test driver that blew up with that configuration versus the actual flight code? Do you know where the problem? I mean, if somebody wrote a unit test that didn't properly
account for the... Right. Right now, the analysis, right. We could, if we knew that that could be the cause of the problem. Right now, we're not, looking into, just basically the system test failed and something happened to the system. If we can work more closely together, like we have, I think the system will grow more intelligent as you tell it what to look for in terms of the different system behaviors and so on.
That just dawned on me that some of those large numbers, if the unit test was coded in a way that didn't accept those.
Oh, okay.
It depends how the unit test is, because that's got its own configuration space.
In
a sense.
Right. Right. Yes.
Did you say what target you were running on for the CFD?
You're talking about the operating system and the environment that's running on. Right now, we're running it on Linux, just because it has CFE has a nice build file and uses the GCUP, which is a Unix tool, GCC. So that's what we're working on. But the SCO system, actually, the client itself has the ability to identify itself with the operating system version, the library versions, and any sort of information that's relevant. And then the SCO server is intelligent enough to assign configurations that are related to platform and hardware to the specific assets that can handle the testing. And we are thinking about using virtualized environments and maybe even some RTEMs, for example, to perform testing that are more hardware and platform specific. Okay, yes?
You mentioned that you're doing your testing on Linux. Do you have any considerations of building CFE for other platforms and trying to collect that information on other platforms? Like maybe using Wind River coverage tool, Rise or something like that.
Right. I mean, that's definitely can be added to the things we'll look at. So we want to prioritize what will we get for the most bang of the buck. So a lot of the issues are probably platform hardware specific. So we might not invest as much energy into building it for a specific hardware platform. But if that becomes a high priority, it's definitely built into the SCO system to handle. And it's built into the iTree to handle this kind of analysis.
And then did you look at all at doing testing on the actual build system itself, like name file, the various options that you can set up at that level of configuration?
No, we have not. Yeah, so right now we only focus on that one CFE platform config file.